Cool. Yeah. Thanks so much for having me. It's lovely to be here to speak to you all. So shall I share my screen?
Yes, please.
And everybody see that okay? Is the key question.
Yes, it's good.
Good. Awesome. So yeah, thanks so much for having me. It's really lovely to speak to you. This talk is not, I kind of got invited to talk about the paper, but I thought I'd kind of give a general overview of one of the kind of most important questions we have in planetary science, which is where did Earth's oceans come from? And sort of some of the ideas we used to have in the past, some of the sort of new observations that have led to changes in some of those ideas, and how some of the work we've been doing here at Glasgow have been sort of like building into this debate, building our knowledge up about why Earth is such a nice habitable place to be, but also then, like, how do you build habitable worlds? Where is water in solar systems across our galaxy? And this is kind of an important question to answer. And I'll start this talk by an old proverb from the ancient mariner, which is water, water everywhere, but not a drop to drink. It's basically the lament of a seafarer becalmed at sea on an ocean voyage with freshwater supplies running low, surrounded by an ocean of the stuff, but unable to drink any of it because the saltiness would result in them all going mad. And so that kind of itself maddening idea that you're desperately thirsty, need fresh water to survive, surrounded by this stuff, but are unable to access it. That lament, I predict, will be as true for future astronauts as it was to ancient seafarers. So, for example, astronauts on the moon, we know now there's growing evidence that lunar rocks have hydrated minerals inside them that are full of water. So an astronaut standing on the lunar surface could be staring out at a surface that he knows is full of water, has a substantial amount of water in it, but is unable to access it. And water for sort of astronauts is critically important, not only for those astronauts to drink, but also you can split it up to make oxygen and hydrogen to make rocket fuel. So being able to find sort of renewable, sustainable reservoirs of water across our solar system, across our galaxy, is going to be critical for human space exploration. I'd also like to start off with this image in any talk because it's incredibly pretty, but also possibly one of the most important images ever taken. This was the Earthrise image taken by the Apollo 8 astronauts in orbit around the moon. And this was the first image taken by a human being of our Earth looking back from sort of like the sort of near sort of orbital environment surface of another planetary body. And this image, I think, people have expressed this way better than I have, has changed something in the human psyche and the way we view our planet. The year after this was the first Earth Day. It basically launched the environmental movement because we basically see this planet, our own planet Earth, from a distance, see that it's a very delicate blue-green orb. It's a very special place for us. It's a very special place in the solar system. It's also a very nice place for us to live. So we should want to protect it and preserve it and keep it that nice, special place. However, if we look out into our solar system, Earth is very much the odd one out, particularly amongst the terrestrial planets, but also kind of further afield. It is the only planet that we know of that has liquid water stable at its surface. It's also, as far as we know, the only planet in our solar system that has life. Not on it. Okay, we haven't looked very hard or for very long or very far away, but so far Earth is the only planet that has life on it. And ostensibly, the other three terrestrial planets in our local neighborhood are really bad places for life to be. Like Mercury has this kind of temperature flux from the sort of near side facing the sun to the far side facing away from the sun, where temperatures are incredibly hot facing the sun and very, very cold facing away. It's lost all its atmosphere, all that atmosphere has been stripped away. So it's an incredibly sterile environment. Venus is even worse. It's basically hell with sort of surface temperatures that melt lead and raining sulfuric acid. It's also lost a lot of its water from its atmosphere. And so it's essentially a nominally dry world now from this kind of runaway greenhouse effect. And then Mars, on sort of a bit further out, is much colder, it's much smaller. It's also lost substantial amounts of its atmosphere, though not all. And again, it's sort of basically a cold desert. It's very dry now. Water is not stable at its surface. So Earth's really the only game in town where liquid water is stable at the surface, and that has basically built what we think of, what we're looking for to try and find life elsewhere in our solar system, elsewhere in our galaxy, because life as we know it relies on water. So basically defining 60 years of NASA, ESA, JAXA policy is go follow the water, go try and find where we might find water in the liquid form, and hopefully there we'll find life. But it also kind of raises an important question: is we have 4 planets in the inner solar system and only one of them has liquid water at its surface. So how do planets get water in the first place? How do you build a habitable world? This is a lovely image from the ALMA telescope, because basically to answer this, we need to go back to look at when planets are forming. And this is an image taken by the ALMA telescope of a protoplanetary disk, a swirling disk of gas and dust around a young star in our galaxy forming right now. And you can start to see these like wonderful structures, these ring-like systems, which, you know, there's a variety of explanations for those. It could be that they are sort of like planets are forming in those rings, clearing out their local neighborhood, but it could be sort of like dynamic instabilities in that gas disk generating these ring-like systems. But potentially for our purposes, for exploring where water is and where water can be, it's the temperature dichotomy that's important. Basically, the closer you are to the sun, the hotter it's going to be, and the further away you are from the sun, the colder it's going to be. Revelationary scientific observation, scientific insight there, I know. But basically that gives rise to a very important feature in any protoplanetary disk, and that is called the snow line. It's basically a sort of line within our solar system, inside of which water is in the gas phase, sort of like clouds of water vapor, and outside of which it's solid ice cubes. Oh, sorry, there's been a glitch here. Ice cubes. So outside the snow line, solid ice. Inside the snow line, water is in water vapor. And the sort of young energetic sun, what it does in that inner solar system region, those gases all get blown out by those young energetic solar winds into the outer solar system, or are indeed lost to interstellar space. What that means for the Earth is we are unfortunately inside that snow line where we are forming. So the nominal idea is that water vapor gets lost to the outer solar system during planet formation. So that our poor Earth should have formed relatively dry. It should not be the nice blue ball of water that we see today. So something else must have happened. The question then is, where did Earth get its oceans from? Where did it get its water from? And if it can't have got it from the region in our solar system where it's accreting, it must have got it somewhere else in space. And so it's looking out into our solar system to try and find other water-rich bodies in our solar system that we can identify that may have delivered water to the Earth. Very quickly, the way we kind of try and track and measure those is to measure the ratio of deuterium versus the ratio of hydrogen. So basically, deuterium is just hydrogen, which has an extra neutron involved. So it's like let itself go a bit, put on a bit of weight. And hydrogen is just that single proton with an electron orbiting around it. Both behave in exactly the same way, but the ratio between those two can give us a window into basically what environment that hydrogen formed in. And when it binds up with oxygen to produce H2O, it gives us a window into what that water reservoir, what that water source was. So for example, the sun loses a lot of its deuterium due to sort of like nucleosynthetic processes. So it's predominantly made of hydrogen. So the vast majority of the sun is made of hydrogen. There's very little deuterium in there. However, in interstellar space, in these giant molecular clouds, there's all sorts of interesting neutron reactions going on. And so you suddenly end up with a lot more deuterium going on there. So your sort of water, any water forming in sort of like giant molecular cloud type things is going to be much more deuterium rich. And so we can measure the ratio of these two isotopes of the same element to try and figure out where our water is coming from and what mixture we might need to produce any given water reservoir. So this kind of brings us into a very old model where we looked out into our solar system and trying to identify lots of water-rich things that we can throw at our terrestrial planets after they have fully formed. So we think, okay, our planets formed dry because of that snow line. We formed inside the snow line. We shouldn't get any water during planet formation. We need to add it later. So we identified comets and we identified asteroids. Certain asteroids are very water-rich. And we go, okay, cool. We just throw those at the terrestrial planets. add the water that way. Earth just must have got a bit more than everywhere else, or the other planets have lost it in some way. That's cool, that's fine. We then kind of made the mistake of going out and checking our answer by going out and measuring some of these cometary objects, because they were kind of the front runner for a long time. They had lots of water. And Comet 67P was visited by the Rosetta mission, but we also have data from the Stardust mission to Comet Wild 2. And when we measure the water composition, the hydrogen content of these objects, the data from the Rosetta mission was provided by the Philae lander, which you may have remember was the really unfortunate probe that went down onto the comet, bounced a few times, ended up in a sunless cave, which was bad for a poor solar-powered little robot. But in the time it was active, in the short span of its battery life, it was able to beam back a compositional measurement of the hydrogen in Comet 67P. And it is wildly different to the water we see on Earth. It's way, way heavier in deuterium. And that kind of threw out that old model of, okay, we just throw comets at the Earth and get our water that way. If you throw any comets anywhere near the Earth, our water ratios on Earth should be wildly different than they are. And so sort of, this is kind of paraphrasing how this whole system worked, but we then kind of looked out, sort of, okay, we can't throw comets at the system because that will not produce the Earth's oceans that we see today. But let's reassess that idea that planets don't receive water during the planet formation process. And luckily, we have an asteroid called Vesta in our asteroid belt, which is basically a failed planet, a protoplanet. It started to grow, it started to differentiate into a core mantle crust, but it didn't go all the way. It didn't clear out its local area, and it's still relatively small. It also has two whopping great impact structures on its surface. This, I'm not sure if you can see my mouth. This is the kind of sort of central uplift of one of these massive craters that sort of compacted and compressed Vesta into a more oblate spheroidal shape. And these images are all taken by the Dawn mission. And that kind of idea, that's going to be a lot of material booted out into the asteroid belt, into the solar system from those giant impacts. And we have meteorites on Earth that we know now are from Vesta. We have been able to sort of compare the spectra beamed back by the Dawn mission to compare it to the spectra we can get off these rocks, and they are very similar. But even more exciting, we have the Alma-Sitta meteorite, which recently fell. Is that right? I think it's, oh, maybe not. Anyway, there is a meteorite that fell, but we actually observed the meteoroid in space a few days before it landed and captured it on camera, captured that fireball, and then went and collected this rock. And it was one of these howardite euclide diogenite type meteorites. And the orbital information we could get from observing that fireball and the imaging we could get of the meteoroid in space tracked it back to Vesta. So we know these meteorites come from the asteroid Vesta. They also have minerals inside them that are rich in water. So it suggests that these protoplanets were receiving water during planet formation. And when we measure that, the hydrogen inside those, it looks very similar to water-rich asteroids, which we also have samples on Earth in the form of the carbonaceous chondrite meteorites. So when we measure carbonaceous chondrite meteorites and the hydrogen inside those, it is almost an exact match for the hydrogen inside the asteroid Vesta. So this is then quite exciting. It presents a new model that actually, our planets didn't form dry. During planet formation, they were being sort of impacted or having material delivered from sort of an extraterrestrial source into the form of these water-rich asteroids. So a portion of our mass, portion of the Earth's mass was accreted from water-rich material. So Earth should start off with some water, and that water is from these water-rich asteroids. And that has led to several really, really important missions, basically trying to tuck into this question. So we've got the Haybausa 2 mission to the asteroid Ryugu, which brought back about 5 grams of material last year. We've been really lucky here at Glasgow to be sort of working with that material as well, and I've got a few grains to measure. We've also got the OSIRIS-REx mission, which is a NASA mission to the asteroid Bennu, which will bring back material in 2023. We'll hopefully get a lot more material because they couldn't even close the sample canister because they'd captured so much stuff. So that's going to be great. So we're going to have these pristine, water-rich asteroid type material to measure on Earth that hasn't been at all affected or contaminated or altered by being on Earth in our kind of very oxygenating environment, very wet environment. So that's going to be really important to help us answer some of these questions. However, the next thing I should kind of say is, okay, cool, we throw these water-rich asteroids at the Earth during planet formation. How do we get them there? Because remember, with that snow line, these water-rich asteroids should be in the outer solar system. Beyond that snow line, Earth's in the inner solar system. How do we get those two types of objects to meet? How do we bring all that water-rich stuff from the outer solar system into the inner solar system? Which brings me to possibly my favorite hypothesis in all of planetary science, which boils down to throw Jupiter at all your problems and hope they go away. Its official title is the Grand Tack hypothesis. And normally you have this sort of compositional dichotomy. You have your dry S-type asteroids in the inner solar system, your C-type water-rich asteroids in your outer solar system. Jupiter forms early, and then by gas drag migration, wanders its way into the inner solar system, nicks all Mars's stuff, so explains why Mars is small, probably disrupts Vesta's accretion, so meaning Vesta becomes a failed protoplanet rather than a planet in its own right. And thankfully for the rest of us further in the inner solar system, Saturn also accretes early, and through sort of gravitational resonances, drags Jupiter back by the scruff of its neck, saying, okay, that's well enough of that, and brings it out to where it is in our solar system at the present day. Simultaneously to that, disrupting all the C-type asteroids in the outer solar system, spinning them into the inner solar system, turning the inner solar system into a pinball machine where all the terrestrial planets are getting impacted and accreting this water-rich material. This is a really cool idea. It explains a lot about the structure of our solar system, like why is Mars much smaller than the rest of the terrestrial planets when, based on where it is, it should have got much more material. Why do we have an asteroid belt that's a whole jumble of lots of different things rather than a nice sort of stratigraphic column? And it could all be explained by this early migration of Jupiter in and out of our inner solar system, kind of upsetting the apple cart, as it were. But back to the Earth, how does that idea of throwing water-rich asteroids at the terrestrial planets reconcile with the water ratios of those deuterium hydrogen ratios that we see on Earth? And that brings us to what I like to call the problem graph of deuterium hydrogen ratio. And I've not put any units on this, but this is just kind of a graphic to give you an overall idea about this kind of issue here. The Earth sits at this nice kind of middle point. And then when we take the average of all the water-rich meteorites and all the water-rich asteroids we've measured so far, relative to their relative abundance in our asteroid belt, they are, on average, slightly heavier than the water we see on Earth. They're slightly more deuterium-rich. That's not to say they all are. There are some types of CM carbonaceous chondrites that sit exactly on where the Earth sits, and that's nice. But if you take all the CMs, all the CRs, all the CI chondrites, all the water-rich stuff that has enough water to matter, and you add all their deuterium hydrogen ratios together and form an average, it is slightly heavier. So water-rich asteroids are potentially not the only story to produce Earth's oceans. We need something else. Vesta is a bit water poorer, but has that sort of similar water-rich asteroid isotope ratio, which is nice. So kind of Vesta seems to be relatively consistent with an origin of water-rich asteroids in the water that's inside it. Comets are really high, they're way off. And so you basically cannot add any cometary material or very, very small percentages to the Earth. Otherwise, our deuterium hydrogen ratio would be really high. The reason this graph's a problem graph is because all the water-rich things we have now identified and measured are all heavier than the Earth. So you can't mix three heavy things and get a lighter thing. That dynamically just doesn't work. So you just get a moderately heavy thing rather than the slightly lighter isotope ratio that we have on Earth. In fact, the only thing that's rich in hydrogen that is on the other side of the graph is the sun, which is problematic for its own reason, because I'm not about to suggest that we throw the sun at the Earth to generate Earth's oceans, because that would be bad for everybody involved. But it essentially illustrates this point that we have a mass balance problem. We have a load of heavy isotope rich water bodies. But we don't have anything on the other graph that has enough water in it to be able to balance that book out, to be able to reconcile Earth's ocean composition. And that's basically sort of led to this sort of a new idea, a new model that, okay, most of our water's got to come from water-rich asteroids, but we need another source of water in our solar system somewhere to give us a light isotopic component to reconcile Earth's ocean composition. And the first port of call was readdressing that idea of, do we lose all the water from the inner solar system? Is there no way we can get that water into planets during the solar nebula stage? And this is some work that my colleague Lydia Hallis has done, basically looking at rocks from the very deep mantle, from a place called Baffin Island, which is sort of like a rather large island in Canada. And rocks there have basically been brought up from essentially the core mantle boundary. They're relatively old. And what Lydia was able to do is get some samples of these and identified what we call melt inclusion. So basically small droplets of melt that are contained within large olivine silicate minerals. And that melt formed in the deep mantle and then was captured in this crystal and brought all the way up to the surface. So what we can do by measuring those melt inclusions is we can get an idea about what the water composition is like in the primitive deep mantle, and so what Earth might have accreted with. And these are some graphs that she produced of measuring these melt inclusions from Baffin Island. To simplify some of these numbers, we've got sort of the delta deuterium. This is the average Vienna mean ocean water composition. That is where the Earth is. Asteroids and comets are way off, the sun's way down there. And Baffin Island samples all plot on this lighter end of the isotope range. So Baffin Island, primitive deep mantle of the Earth, seems to be more isotopically light than the water we have in our oceans, the water we have at the surface. What that suggests is that the water we initially accreted with had a lighter isotopic source. And the sort of explanation for this is potentially that solar nebula, which would have a very similar isotopic ratio in terms of deuterium hydrogen to that of the sun, can actually somehow get into planets, even though we're inside that snow line, even though water's in the gas phase and getting lost. And while this is very hard to do, people have suggested that potentially, as you've got this accreting planet sort of surrounded by this water-rich gas, hydrogen-rich gas, you basically can diffuse it into that planetary body during planetary accretion, and that's one way you could get some of that light water into the early Earth. And another way you could do it is if you have all these dust grains with sharp angular boundaries on grain boundaries, you could sort of condense and sort of produce little droplets of water on the edges of these grains, kind of like the effect you get from a blade of grass in a field. You get dew forming on it in the morning, and then as those dust grains go into the early Earth, you can accrete to the Earth. They can sort of add some water that way. All of those things are incredibly hard to do. And so this idea is around. It's a really cool idea. It'd be great if we could get some water in that way, but sort of the mechanism to do that, I don't think is quite nailed down. So we kind of need a model to like 1.3 now where, okay, we could get some from the solar nebula gas, maybe not enough to balance the water-rich asteroid component. We need something else. We still need this additional isotope reservoir. And this is where sort of the work so I've been doing, as well as my colleagues in Glasgow, as well as my colleagues at NASA, Hawaii, Curtin University in Australia, a whole bunch of people have come together to make this sort of study happen. And that is looking at a really cool phenomena called space weathering. Now, space weathering is a combination of a variety of processes. It's like this catch-all term from the solar wind, which is a stream of hydrogen and helium ions from the sun, as well as ultraviolet rays from the sun. We also have micrometeorite impacts, so small like dust-sized grains zipping around up there in space, impacting surfaces in the sort of vacuum of space and damaging them, as well as galactic cosmic rays, which are these incredibly highly energetic particles ejected during sort of like the deaths of giant stars. And all of these processes come together to damage and destroy and alter any mineral surface, any surface that is exposed to the vacuum of space. So that's stuff like surface of comets, the surface of Mercury, the surface of the moon, a billionaire's car, apparently, is also a thing that's being affected by space weathering, as well as the surfaces of asteroids and the surfaces of any little dust grains that are flying around up there. The reason I chose this image is this is the asteroid Itokawa, which is the grains we used in this study, which I'll come to in a little bit. What space weathering does, this is an image from John Bradley's study over in Hawaii in 2014, looking at one of those little tiny dust particles, or known as interplanetary dust particles, that have been affected by space weathering. You see loads of really interesting features. You see these beautiful cosmic ray tracks from those highly energetic particles just blitzing their way into the sample, producing these sort of very long damage lines as they pass through. You also get these tiny iron metal nanoparticles starting to form there. You're destroying the crystal lattice, you're amorphosing it, you're turning it into a glass. But kind of one of the key observations, you're starting to generate a bunch of these vesicles or bubbles in the outer surface. And this surface damage layer is only about 100 nanometers to 200 nanometers thick. So it's a really thin layer and a really delicate layer. What John and colleagues did in 2014 was using VELS, which is valence electron loss, energy loss spectroscopy, to measure the composition of the gas inside some of those bubbles. And this is the result they got. I don't worry too much about this spectra, except for this little bump just in here is very typical of the presence of an OH bond. So basically the presence of hydroxyl, and we use hydroxyl very much as an approximation for water. So this sort of study very much showed that in the outer surfaces of space weather material, you're potentially starting to generate water. This has now been done by shown by experiment as well. There was another study irradiating surfaces of these surfaces of minerals with a sort of basically a proton beam, and then sort of evaporating off the gases that formed in that surface. And among those gases was water as well. And this kind of brings me to kind of one of my favorite equations in planetary science now, is the sun produces the solar wind, which is a stream of protons. If you take those protons and add them to rocks, you produce water in the outer surface, which is really cool. And the mechanism, I think, still needs to be relatively more precisely constrained, but essentially it's that hydrogen comes into your silicate mineral, nicks an oxygen, boots out the cation like iron or magnesium, which go away to then produce your iron metal nanoparticles, binds with that oxygen to produce water. Another hydrogen ion comes in, and you get H2O in that outer surface. So over time, you start enriching that surface in water through the solar wind. That then brings us to sort of the start of 2017, which is when I started my first postdoc, and the start of this study to kind of explore the space weathering process to try and figure out how much water you can basically put into particles through this process. So the Itokawa mission, the Haybausa mission, which is visited the asteroid Itokawa, was a Japanese space agency mission that returned 1,500 whole particles from the S-type asteroid Itokawa in 2011. All these particles were about the width of a human hair. And this whole mission was amazing in terms of a feat of engineering where literally everything that could go wrong seemed to go wrong during this mission. And yet they still managed to succeed in the goals of the mission, which was to bring back material to the Earth. I think there's about like 13, 14 films made in Japan about the trials and tribulations of the science team and the mission team during this mission, and sort of like losing connection, losing communication with the thing on its way there, not knowing if there was any actual material inside because the landing touch and go experiment had to be aborted several times because there was larger rocks nearby. But anyway, amazing mission, brought back 1,500 particles, all about the width of a human hair in 2011. I hadn't started my career then, I was still doing my undergraduate degree, so this all kind of passed me by. But in 2017, JAXA announced their fifth announcement of opportunity to come study these grains. And that's when I just started my first postdoc here at Glasgow. And so I was like, wow, this is a really cool opportunity. These are some of the most exciting samples around right now. We have to apply to try and get some samples. And we've got this new tool that we can apply to try and study this kind of space weathering process in detail. I didn't hold that much hope for this application because the technique that I'm about to describe to you is a destructive technique and would literally destroy these grains one atom at a time. So I was not holding out much hope that they would give us any material, particularly as I was a first year postdoc, not kind of had a proven track record of working with this kind of material, let alone destroying this stuff. But they gave me 3 grains, which is 0.2% of the total mass returned, which was very generous of them, particularly as I was about to tear them apart one atom at a time. They're really, really small. These are kind of the 3 grains we got. This is a human hair for scale. So all of these were on the scale of a human hair, which then presented a new problem for me, which is the stress of trying to pick up tiny, tiny dust grain by hand. Thankfully, I had a really nice training course at NASA Johnson Space Center to sort of train me in picking that up. That helped in terms of the technique, but it didn't help in terms of the stress level. I sort of practiced for hours and hours and hours picking up a bunch of tiny dust grains of basalt from the Earth, which didn't matter, until I could get 10 out of 10 out of 10 on the end of a needle. And it was a huge sigh of relief when we managed to get these things mounted up on the end of the needle to study them in our microscopes, which was just a lot of nightmares, a lot of stress, but very glad that I didn't have to call JAXA up and say, hey, I've lost one of your precious grains. I breathed it in, even worse. They're all safely now mounted up and we can study them. And the next challenge was I will still collaborate a lot with Curtin University in Australia. And the technique I wanted to use is called an atom probe. And at the time, they were the only geoscience atom probe dedicated facility in the world. I also did my PhD there, so it was a natural place to want to go and study these grains using this atomic scale technique. However, that presented its own challenges of traveling through airport security with priceless asteroid dust. So JAXA does an amazing job of sending you these things in very robust Pelican cases, and the sample storage facility is incredibly secure. It's incredibly tight, avoids any contamination. However, from the perspective of an airport security person, it also looked dodgy as hell. So that led to many, many conversations because, of course, I'm not letting this thing out of my sight. It's not going in the hold. It's coming with me. It's sitting on my lap all the way through the 24-hour flight. It's literally more than my job's worth if I lose this stuff. But of course, it goes through the X-ray scanner. They immediately pick it up, to which I immediately respond, please be very careful with that. Don't drop it. It's very delicate, which from their perspective is an alarm bell immediately. And they suddenly get a bit more on edge, thinking, why don't you want me to drop this thing? What's inside it? And to which they go, can you open this, please? And from my perspective, it's like, no, I don't want to open precious asteroid dust container to contaminate it with airport. Please, can I not open it? Which obviously doesn't help my situation from their perspective. Sort of asking me what's inside, and sort of starting to you can see them reach for the little red button to sort of send in the cavalry. But then I kind of throw them a curveball by being honest and saying it's little bits of asteroid dust. Here's an email from the Japanese Space Agency explaining everything, and then you get a sort of another whole series of kind of an awkward 5 minutes as they read that email, initially deeply skeptical, eventually getting kind of a bit confused, and then really excited as they think, hey, maybe this is a real thing. And then they start answering all the same questions over again, but in terms of, I want to see the asteroid dust, to which my answer is, well, still no, I still don't want to open the dust. It's very precious. It needs to be kept in a clean environment. I've also been talking to you for an hour now, half an hour being grilled as a threat to national security and half an hour being grilled because it's really, really cool, these samples, and I need to catch a flight. So fortunately, made it to Australia with all the grains intact, all nicely mounted up, and we were able to get them into the atom probe. So the atom probe tomography is an amazing tool. It's relatively new in geoscience and planetary science. It's been sort of applied in material science for decades now. And the way it works is you put a very, very fine needle that's about 100 nanometers across in a very high vacuum, apply a very high voltage to it, and then shoot it with a laser. What that does is it gives your sample just enough energy for one single atom to be ionized and fly across that potential difference and hit a position-sensitive detector. What that allows you to do is, from the time of laser pulse to the detection, allows you to figure out what element it is, what isotope of that element it is, where that atom was in your sample to subatomic precision, And it's also been shown recently to be able to detect molecules, and those molecules be kind of indigenous to the sample. And one of the molecules that's really exciting that we can measure with the atom probe is water. So that was the kind of reason for wanting to do this. We could quantify and show in 3D the spatial distribution of water molecules in your sample. So for example, this is an atom probe data set of just a meteorite. Each one of those dots rotating around there, there's 23 million atoms in there. Each one of those dots is a single atom that we measured. They are color-coded based on what element they are. And these little red dots that are kind of rotating around, they are nano nuggets of platinum. They're about 1 nanometer across. There's about 100 atoms total of platinum inside them. So it kind of shows you we're getting literal atomic resolution of materials using this technique. To give you an idea of scale, we'll bring back the human hair that I've been using throughout this, and I'll put a little red dot onto the surface of that human hair, which would be the sort of diameter of an atom probe needle. So it's there now, and hopefully, unless you've got a 4K screen, you can't see that little red dot. We're talking really small samples. And what we were hoping to see using this technique, if we look at that outer space-weathered surface, the idea is we've got this sun producing a solar wind, and if we put a rock in space, over time, the surface of that rock will become sort of enriched in water. It will have sort of like water in that near surface of that material. A more serious example is sort of like this is sort of like a model of our dust grain. We would expect that outer few hundred nanometers to become enriched in water. And the great news is that's exactly what we saw in our Itokawa data. So this is our Itokawa data sets. The gray atoms are a protective layer of chrome that we put on the surface of our sample to protect it. And so to make sure during sample preparation, we didn't destroy the space-weathered surface that we were interested in. And we could also then know when we hit that top surface and hit that to make sure we were measuring the surface of the grain. These two data sets are showing either the distribution of H2O molecules in blue or the distribution of OH molecules in teal. And the really interesting thing is we see an enrichment, concentration of H2O and OH molecules in the outer surface of that grain, which is exactly what we would expect to see on the surface of a space-weathered grain that's been exposed to the solar wind. However, you could argue that that could just be contamination, some sort of atom probe effect, and we wanted to make sure that this result was robust. And so we measured two standards alongside this analysis. One was just a bog standard mineral of olivine that we'd left in the lab, prepared a sample from the surface of that grain and measured it. And in that sample, we saw no enrichment at the surface. So that's good. There's no increase in water content at the surface of this grain. So olivine isn't just naturally abundant in water at its grain boundary or grain surfaces, and it's not an atom probe effect. Possibly the most critical measurement we made is our colleagues in Hawaii and Idaho National Labs irradiated a sample of olivine using a deuterium ion source. So they fired deuterium, that heavy water ions, at our sample, at an olivine grain. And then we got that sample at Curtin and we measured the outer surface of it. And what we saw there was deuterium oxide and heavy water, so D2O. What we didn't see was OH and H2O. So what this really nicely showed is we were seeing an enrichment in the molecules that we'd irradiated with. They do produce water, in this case, heavy water in the outer surfaces of grains, but it's not a contamination effect of being just a space-weathered surface having absorbed water, because we don't see any of the OH and the H2O that we would expect if we saw that, because we didn't put water anywhere near this sample. So that gave us confidence that our results in the outer surface of those Itokawa grains is a real water source, and it's from the solar wind. So kind of sort of nice graphical representation that was produced by Curtin for this study is showing that the solar wind process, we can measure dust grains that have been affected by space weathering to identify concentrations of water in their outer surface. What we were then able to do is start sort of making some fun interpretations and some fun sort of figure out some implications of this result. The first of which is, okay, how much water can you pump into a grain of a certain size? And so we kind of modeled the sort of particle size versus sort of width of your space-weathered surface and how much water could you actually get into it. And obviously for something the size of an asteroid, really not a lot. But for grains that are sort of sub 10 microns, so sort of 10,000 nanometers in diameter, you are able to start enriching that material in water from the solar wind up to about an atomic percent. So that is a lot of water that you can start pumping into tiny dust grains. We can then figure out how much water could we put into Itokawa itself, into the soil regolith on the surface, because we know the grain size from the material that's been brought back, and we know the width of the space weathered surface. We know how much water we're able to put into that space weathered surface, how much water is in, say, a meter cubed of regolith from the asteroid Itokawa. And it turns out there's about 20 liters, which is not a huge amount, but it's still quite a lot, produced by the solar wind, produced by this reaction process, produced by space weathering. What's really nice about it is it would be very easy to extract this water, which leads me to possibly my favorite experiment ever done in planetary science, which is sort of in the 60s and 70s, they sent some field work, some sort of field geologists out onto the moon to collect some rock samples for us, and they brought them back to the Earth. And then at some stage, someone got permission to put some of that precious lunar dust in a microwave, which was an amazing experiment, really kind of out of the box, but also in the box thinking. I hope you saw what I did there. And what happened when they turned this microwave on was the lunar soil melted, which was a surprising, but also not surprising observation, because, as I mentioned before, these lunar dust would have also been affected by space weathering. It would have these iron metal nanoparticles in its outer surface. If anyone knows anything about microwaves, one of the cardinal rules is do not put metal inside it. And so this metal inside these lunar soil grains heated up the samples, resulted in them melting. And so any water produced by the solar wind in that lunar soil would have been immediately released. So you could potentially extract water from the lunar soil, from the lunar dust, or indeed soil from any airless world, any asteroid in our solar system or our galaxy, and extract that water. It's also a renewable, sustainable resource because until the sun stops shining, it will always be producing a solar wind, always producing water in the outer surface of these grains. And kind of going back to the Ancient Mariner, that is really good news, kind of looking out. NASA is really serious about building this kind of Artemis base camp, permanent human habitation system on the lunar surface. Those astronauts are going to need water, the rockets are going to need to be fueled. And if you can use the lunar soil as a resource for water to split to rocket fuel, but also to give your astronauts a drink and any sort of hydroponic system to produce plants, lunar dust might be an ideal kind of material to generate that water. It also kind of kills two birds with one stone. If you talk to any astronaut that's been on the moon, they kind of all come back with the same thing, that they could overcome any technological, physiological challenge that they were faced with walking on the moon, except the dust, because it just got everywhere. It was really annoying, had lots of annoying properties, and started wrecking like lots of their equipment, lots of their electric. So with a simple microwave oven, you could not only get water to drink, but also change the lunar soil into something more amenable and less irritating. It's also very important, obviously, thinking of even further ahead in terms of resources, in situ resource utilization, looking towards asteroids as resources and looking at their soil as this sort of resource for water to act as stepping stones out into our solar system and beyond. So that's all cool. But the key question of this talk is to answer the question, what about Earth's oceans? Where did Earth's oceans come from? And what does this space weathering of small grains have to do with that? And basically, the observation that teeny tiny grains in space exposed to the space weathering processes will slowly become enriched in water over time. So anything smaller than about 10 micrometers in diameter will be about 1% water from space weathering in its entire mass, which is a sizable amount of water. It also kind of gets you thinking about, okay, on Earth right now, what is the distribution of mass of material hitting the Earth? So we get 50,000 tons of extraterrestrial material hit Earth every year. Meteorites, believe it or not, so stuff about the size of your fist, are an incredibly low percentage of that mass flux, or annual mass flux. Comets and asteroids, so bigger objects, are a bit of a kind of a higher percentage of mass flux, but still not much. And thankfully, they don't happen very often. But when they do, they add sort of an appreciable amount of mass in one go. By far and away, the biggest contributor by mass, to the tune of about 99% by mass, is tiny, tiny dust grains on the order of 10 micrometers or smaller, maybe a bit bigger, to the Earth. So these tiny dust grains are raining out of the sky at us all the time, producing these beautiful sort of like shooting star displays. And in the past, that distribution has remained pretty constant. So even during planetary accretion, we would expect the majority of material accreting onto the proto-Earth to be tiny dust grains alongside sort of some larger asteroids and comets. All that tiny dust grains, as soon as the solar nebula gas has gone away, will be affected by space weathering, will start to get water embedded in its outer surface. So what we then did was kind of model the sort of various ratios of different reservoirs, different water-rich asteroidal bodies, even some less water-rich asteroidal bodies, with this sort of like solar wind derived water component in tiny dust particles, to figure out what mixtures we would need to generate Earth's ocean composition. And there is a big range. There is a big range, but on average, you're looking at about a 50-50 ratio of tiny, tiny dust particles affected by the solar wind to water-rich asteroids. So going back to our problem graph, we might potentially have a solution to this water-rich light isotopic reservoir of tiny dust particles that you can add alongside your water-rich asteroids to the Earth to generate Earth's ocean composition. And a 50-50 ratio of water-rich asteroids to tiny dust particles might be what you need to produce Earth's ocean composition, which led to this really nice analogy that basically half of the water on Earth is made from sunshine, which kind of gives you that extra motivation to try and get those 3 liters of water you need a day that sort of doctors prescribe. I think half of that is was originally sunshine, which is nice. It also kind of makes you think about, okay, if I was standing on a proto-Earth looking up at the sky, you'd see these big water-rich asteroids raining down on you, but also this absolutely gorgeous sort of meteor shower show as these tiny space-weathered dust particles rain out of the sky as well, producing this brilliant light show. It also means that it's not just Earth that would have got water. Venus should have got a lot of water by this mechanism in its early history and has since lost it. And indeed, there's been growing evidence that Venus, in the sort of early part of its life, 4.5 billion years ago, might have been a much more water world before it went full greenhouse. And you should never go full greenhouse. Mars, similarly, there is more and more evidence, there are particularly those beautiful big canyons, that 3.7 billion years and older, Mars was a much different planet, had these sort of like northern hemisphere oceans, had lakes and rivers and canyons. So all our terrestrial planets probably were given or delivered water from water-rich asteroids and tiny dust grains, and maybe a bit from the Solar Nebula as well. It also means, as we were discussing just before this talk, that basically every planet in our galaxy got some water this way. So getting water into planets during planet formation seems to be relatively easy. Keeping their water seems to be relatively hard. But normally, if we're looking to build habitable worlds in our solar system, in our galaxy, this seems to be quite a common occurrence that should happen around any star in our galaxy that has a terrestrial planet in the habitable zone. With that, I think I'm done. I'll just like to thank my collaborators, who is just wonderful to work with all the time to do this really cool work, and without whom this stuff wouldn't happen. And I'll be more than happy to take any questions. Thanks very much.
Okay, all I want to is to clap. Is awesome. Thank you so much. It was extremely entertaining, and the visuals that you have included I really love your clips. Definitely. I wanted to also introduce Judy Alton. She joined us.
Hey, Judy.
in the middle of your presentation, and she's actually from material science, the area of JSC, and I put in the note that most likely you have received the training in one of the areas that Judy is working.
Yeah, absolutely. Yeah. I was really fortunate to get Chris's training course to figure out how to pick up tiny dust grains without dropping them, which is really important for lunar studies and everything.
Judy, you're muted. I'm trying to. Oh no, you're not. But I do not hear your audio. So I see that your mic is active. Anyway, I wanted to thank Luke, as was a really great presentation. I will stop recording, but we still can continue interaction, and any questions are welcome.